Welcome you all to Principles of Organic Synthesis. At present we study free radical reactions. In this topic so far we had one lecture in which we studied the methods that can be used to form free radicals, where we have seen three types of reactions. If you have the weak bond, you can try to homolytically cleave using light or heat. In this way you will be able to produce radicals. Then we have seen you can also try to produce radical by redox process. If you can give electron, you can convert into radical. We have seen some examples, particular we focused on carbon halogen and carbon carbon bond formation. In continuation, in this lecture we will try to see some more examples. The first example involves the reaction of the seleno compound with the alkene as well as carbon monoxide in the presence of light. It can undergo coupling to give this compound. If you look at here, we have seleno compound, which as we have seen, this carbon selenium bond is weak, which can readily undergo homolytic cleavage in the presence of light, and you can form this radical. This carbon center radical can be stabilized by this ester group. Once if we have this radical can undergo addition reaction with this alkene, and you will end up with a secondary radical. This secondary radical now can react with the carbon monoxide. Addition reaction can lead to the formation of the carbonyl radical. Once you form this radical can react with this radical, and you will be able to make a carbon selenium bond. What you do here, you make a CC bond, and you also do carbonylation, this reaction in this way, so you can make a multiple carbon-carbon bond. So three components are coupled together photochemically in the presence of light, and the reaction condition shown here, and you can make this molecule. Now let us look at the reaction of the cyclopentanone derivative. When you react ketone with samarium iodide, it can give one electron to this, and it can lead to the formation of the ketyl radical, where samarium 2 is converted into samarium 3. So one electron oxidation process, and this ketone can be converted into ketyl radical. It can, where samarium is converted into samarium 3. Once you form this radical now can undergo intramolecular cyclization. In this case depends upon the substrate, 5-exocyclization, and you will be able to get this radical. Once you form this radical as again as we have seen can be stabilized by this electron withdrawing group. The secondary radical now can be converted into carbon ion. By single electron transfer process, the samarium 2 will be converted into samarium 3, and then you will have the carbon ion. Once if we have this one, and when you treat with proton source, and it will be converted into the bicyclic compound. It depends upon the stereochemistry of the alkene. When you do this, if you have here E isomer, you can try to cyclize as shown here. If you have Z isomer, you can get this is a ratio of the product. This depends upon the stereochemistry of the alkene, and the crucial step is here, and the samarium has been well explored. The samarium iodide has been widely used for the cyclization of keto compounds. Here it can give one electron, transform to the ketyl radical, and it will be samarium 3. And once you form this radical can undergo reaction, and you get this carbon-centered radical, which can be stabilized by the ester group. Once you form this radical, this can be converted into carbon ion by single electron transfer process, where samarium is oxidized to samarium 3. And once you have the carbon ion, which when you do the workup, you can convert into, you can protonate, you can get this bicyclic compound as the product. Now let us look at another example. Just we have seen the transformation of cyclopentanone into the corresponding ketyl radical using samarium 2 iodide. And here also this reaction involves a beta keto ester. When you treat with the samarium iodide, as just we have seen, it can convert into this keto group into the ketyl radical by transfer of one electron, and this single electron transfer process, and samarium 2 will be converted into samarium 3, and you will be able to form this radical. Once you form this radical, this radical can undergo intramolecular cyclization, and will be able to form a by exocyclization. This is a radical. Once if you form this radical again, as just we have seen, you have the samarium 2, and it will be converted into samarium 3 by single electron transfer process, and you will be able to get anion here. This when you do the workup, and you can get this cyclic compound. You can see here, and as you can see, you need stoichiometric amount of samarium iodide in this reaction. Since 2 electrons are transferred here, 2 equivalent of samarium iodide is required to successfully complete this transformation. So here the intermediate is shown here. So first the samarium 2 can transfer an electron, you form the ketyl radical, and this can be stabilized like this. You form the radical. This radical can now undergo cyclization. Here you form the secondary radical. Once you have this one, this can give one electron, and you generate the carbon ion. Once if you have this one, when you do the protonation, you can convert into alcohol as the product. Here another example shown. Here also the intramolecular cyclization takes place. As just we have seen, now samarium iodide can convert into the carbonyl group into the radical anion by giving one electron. You can convert into the ketyl radical. Once you have this one, this can now undergo cyclization, again 5-exo tricyclization, and you will be able to get this this radical can further convert into carbon ion so which when you do the protonation you can convert into product. Here you make a new carbon-carbon bond between this carbon and this carbon. You make a new bond here. In addition to that, you also whatever the radical you form, you convert into carbon ion, which can be treated with proton source. In this way, you will be able to make a bicyclic alcohol as the product. As you can see here, the radical chemistry plays very important role to construct highly functionalized complex molecules. So far we have seen few examples using samarium to iodide, where you can generate the ketyl radical. That ketyl radical can lead to addition reaction with alkene that can be further reacted with samarium iodide to give you a carbon ion intermediate that can be reacted with the proton source to give the cyclic compounds. Now let us look at the use of copper based catalyst system. Whatever we have seen so far, those reactions involve stoichiometric amount of samarium iodide. You can see here you require only catalytic amount of copper catalyst. Here you need only catalytic amount of copper. This reaction can be facilitated in the presence of di-tertiary butyl peroxide. Here the reaction of toluene with this nitrostyrene derivative shown. So it can couple together, you will be able to form the CC coupled product. You make a new carbon-carbon bond between this carbon of this methyl group of toluene with this carbon. Now let us look at the reaction pathway of this transformation. As just we have seen the case of tributyl tin hydride mediated reaction where you use AIBN as a radical initiator, you can also use di-tertiary peroxide. When you heat, here this reaction has been thermally carried out. When you use light or heat, when you heat 110 degrees Celsius, this bond can undergo homolytic cleavage to form this radical. You form true tertiary butyl oxy radical. This radical also can further convert into, so one of them is converted into ketone and methyl radical. Once you form the tertiary butoxy radical, this radical can abstract the benzylic hydrogen. This carbon hydrogen bond is weak, so this tertiary butoxy radical can abstract this hydrogen and you form the benzyl radical. Benzyl radical is stable radical. This is much stable comparing to alkyl radical we have seen the last class. Once you form the benzyl radical and which can undergo addition reaction with alkene. We have seen several examples. If you have the radical that can lead to alkene which are bonded with electron withdrawing group. Now here the alkene undergoes addition with this radical, then you will be able to get this benzyl radical intermediate. Once you form this radical can be stabilized by this aromatic system due to delocalization. This also you have the electron withdrawing group. So in this way this radical can be formed. Once form this radical, now this can carbon nitrogen bond under these conditions undergoes homolytic cleavage to form a alkene, where you generate NO2 radical. So using a catalytic amount of copper, and you can carry out the reaction. The copper facilitates the cleavage of this peroxide bond. In this case, when you heat in the presence of copper, it can undergo homolytic cleavage to form the tertiary butoxide radical. This radical once formed, as just mentioned, it can readily react with this weak benzylic CH bond to produce a benzyl radical, where the tertiary butoxide radical is converted into tertiary butanol. This radical can readily undergo reaction with alkene to give the benzyl radical. Once you have the benzyl radical, that can convert into this alkene derivative by homolytic cleavage of this carbon nitrogen bond, that can lead to the formation of NO2 radical. In this way you can make beta alkyl styrene derivatives, and as you can see here, and the reaction involves catalytic amount of copper. You can using stoichiometric amount of di-tetrabutyl peroxide, you can carry out the reaction. Now let us look at another example. If you look at the earlier one, we had the nitrostyrene. Here also you have the cinnamic acid. In the earlier case we have seen the involvement of benzyl radical. If you have the toluene, you can try to react with the radical and you can form the benzyl radical. That leads to addition, you get the beta alkyl styrene derivatives. Here the reaction of isopropanol with the cinnamic acid is shown using catalytic amount of copper and tertiary butyl hydroperoxide as accident. So in this reaction, now let us look at the mechanism of this transformation. In the presence of catalytic amount of copper, tertiary butyl hydroperoxide can undergo cleavage. Again you have the oxygen bond which can undergo cleavage, and you will be able to form the tertiary butoxide radical. Once you form the tertiary butoxide radical, this can react with isopropanol. This is well known. It can undergo homolytic cleavage of this carbon hydrogen bond. You form this radical, and where the tertiary butoxy radical is converted into tertiary butanol. Once you form this hydroxy radical, this radical now once you form this radical can undergo addition reaction with double bond. So now the cinnamic acid undergoes reaction with the copper. You use copper 0, undergoes reaction with the copper in the presence of tertiary butyl hydroperoxide. It oxidizes the copper 0 to copper 2. You form the copper to carboxylate. Once you form this one, the radical that you have generated from the reaction of isopropanol and tertiary butyl oxide, which can undergo addition reaction with this double bond as shown here. It can undergo addition reaction as we have seen earlier example. You form a benzyl radical. Once you form the benzyl radical, this carbon-carbon bond can undergo cleavage, homolytic cleavage, to give alkene, where you generate carbon dioxide as a byproduct. The copper 2 is reduced to copper 1. So, in this reaction, as you can see here, the tertiary butyl hydroperoxide plays dual role. First, it is converted into tertiary butoxide radical. It helps to form the radical from the isopropanol. You form this radical. In addition to that, the tertiary hydroperoxide also helps to oxidize the copper 0 to copper 2 carboxylate, which can readily react with the cinnamic acid. We form this copper 2 complex. Once we form this one, now the radical undergoes reaction with this double bond, followed by decarboxylation, can lead to the formation of alkene having this alcohol functional group, where you generate carbon dioxide as a byproduct. The next example involves the combination of manganese 3 acetate and copper 2 acetate. So, when you have this 1,3 dicarbonyl compound, here the ketone is bonded with the sulfoxide. When you treat this compound with manganese 3 acetate in acetic acid medium, it can lead to the formation of this radical. This reaction has been well explored by Professor Molander. He has pioneered in this chemistry. Once you form this radical, and this radical can undergo addition reaction intramolecularly with this double bond, and you will be able to form a tertiary radical. What you do here, you form a carbon-carbon bond that results in the formation of a tertiary radical. This radical can undergo further cyclization with this double bond, and you will be able to get this exocyclic alkene as a product. And what you do here, you form 2 carbon-carbon bonds. It involves a tandem radical cyclization. First, what you do here, you have this hydrogen. This bond undergoes cleavage in the presence of manganese acetate. It can form the enol form. It can lead to the formation of the radical. Once you form this radical, which can undergo reaction intramolecularly with this double bond to form a 6-membered tertiary radical. Once if you have this radical that undergoes further reaction with this alkene, you form a 5-membered exocyclic radical. That radical can now convert into alkene. And in this way, you will be able to make this bicyclic system where you have the carbonyl group as well as you have the sulfoxide substituent. You also have the alkene. You can make this multifunctional bicyclic system using radical reaction. Another example shown here, as just we have seen here, in the place of sulfoxide you have the ester group. When you react this beta keto ester derivative with manganese 3 acetate, as just we have seen, you can form this radical. Once you form this radical, this can lead to intramolecular cyclization to give a six-membered cyclic system where you have the tertiary radical. This radical can now undergo intramolecular cyclization with this aromatic system. Then you will be able to form a multifunctional tricyclic system. First, it undergoes cyclization with this double bond. You form a tertiary radical, which can lead to intramolecular cyclization with this aromatic system, and in this way you will be able to form a tandem cyclization. You make again a two carbon-carbon bonds. First one is aliphatic, another one is you make bond with this aromatic system. It can undergo addition reaction followed by removal of hydrogen. You can lead to the formation of this tricyclic system. You can see here with excellent stereochemistry. So far we have seen the reactions that involve samarium to iodide, copper catalysis, and stoichiometric amount of manganese rheostate. These systems can generate the radical. That radical can lead to intramolecular cyclization to produce polycyclic systems with the excellent stereoselectivity. Now let us look at the tin based chemistry. So when you have the tin reagent, when you irradiate, this also can undergo homolytic cleavage. This bond is weak. Once form this trimethyl tin radical in this reaction. When you heat at 70 degree Celsius in the presence of light, it can form the trimethyl tin radical. Already we know that when you have this trialkyl tin radical, it can readily react with carbon halogen bond. In this case, you have this carbon iodine bond which can undergo reaction and you will be able to form radical. This radical can undergo addition reaction with isocyanide. Addition reaction that can lead to formation of this radical. Once you form this radical, this can undergo exotic cyclization to give this derivative. Once if we have this one, this can undergo further intramolecular reaction with this aromatic ring. In this way you will be able to make a polycyclic system, and which is used as topoisomerase inhibitor. You can see here a complex molecule. What you do here, you make a 3 carbon-carbon bond with excellent stereoselectivity. You can use this tin based reagent which can, if you have the carbon halogen bond, you can readily cleave homolytically to form a radical. Once you form the radical, that can lead to intramolecular cyclization to give carbon-carbon bond formation. Now let us look at another example. This also involves intramolecular radical cyclization. Here the combination of tributyl tin hydride AIBN has been used. Already we have seen, if you have the AIBN, so this can undergo cleavage to form the stable radical, which we use as initiator the radical reactions. When you have this radical which can react with the tin hydrogen bond is weak, it can undergo reaction readily with this radical, and you will be able to form tributyl tin radical. Once you form this radical, it can readily react with the carbon halogen bond. You have the aryl bromide which can undergo homolytic cleavage, and you form the aryl radical. Once you form the aryl radical, in this it undergoes intramolecular cyclization, 5-exoteric cyclization, and you will be able to form this derivative. Once you form this, you will be able to form once you form the radical, now this can undergo homolytic cleavage under these conditions. If you have the carbon sulfur bond, this also can lead to the homolytic cleavage, as just we have seen. If you have the carbon selenium bond, it can be readily cleaved. Once you lead to the homolytic cleavage of this carbon sulfur bond, it can form alkene as the product. So as you can see here, and you can use this radical process to form this highly functionalized indole derivatives. You can see here you have the, and when you use these reaction conditions, you can have like benzylic substituent doesn't affect selectively. The tributyl tin radical react with this carbon halogen bond to give the radical. That radical can undergo cyclization to give the respective product. You will not be able to use here the redox process, because if you use this, you have the benzylic CH bond which also can undergo reaction. Therefore, depends upon the nature of the substrate, you have to choose the reaction conditions. Here the combination of tributyl tin hydride and AIBN is used. This because you can form the tributyl tin radical that can selectively react with this carbon halogen bond without affecting other functional groups. You will be able to form the radical. Once you form the radical, that can undergo addition reaction followed by elimination to give this alkene as the product. Now let us look at another substrate. As you can see here, this also have multifunctional groups. When you use this xanthate ester with tributyl synhydride AIBN, it can lead to cyclization. Professor Zamir Zad is very famous for this xanthate ester chemistry. He has done a lot of work, and when you have this substrate in the presence of tin hydride and AIBN can form a radical. This radical can lead to cyclization with double bond to give complex molecules. Now let us look at here the combination of AIBN and tributyl tin hydride can form a tributyl tin radical. Already we have seen earlier. Once you form the tributyl tin radical, this radical can react this carbon sulfur double bond, and you will be able to form this intermediate. Once you form this one, now it can undergo homolytic cleavage. The carbon oxygen bond to form this secondary radical. Once you form the secondary radical, you have the carbon double bond nitrogen, which can undergo intramolecular cyclization to give this nitrogen radical intermediate. Once we have this one, this can undergo further reaction. This can lose nitrogen molecule, and still being you will be able to form tertiary radical. Once you form the tertiary radical, this can undergo exoteric cyclization to give a radical that can be further converted into, once we have this radical can react with tributyl tin hydride. In this way you can introduce the hydrogen atom here, and you can try to form a polycyclic system. You can see here through the radical cyclization, what you do here, you form two carbon-carbon bond to get this fused cyclic system as the product. Now let us look at another example. This also involves intramolecular cyclization. You have the carbon halogen bond, as just we have seen, and if you have the tributyl tin radical, that radical can be generated from the tributyl tin hydride and EIBN, which can readily react with the carbon halogen bond to form a radical. So once you form this radical can lead to cyclization, and that can form this tertiary radical. This radical can be stabilized by this amide. Usually 5-exoteric cyclization is favored. In this case, the 5-endoteric process is involved. This is the radical because it can be stabilized by this amide group. Once if we form this tertiary radical, this radical now can react with tributyl tin hydride, and you can get this bicyclic lactam as the product. Now let us look at another molecule where it can lead to the formation of this 4-member lactam as the product. Now as just we have seen, the tributyl tin radical can react with this carbon halogen bond. Homolytic cleavage of this carbon halogen bond can lead to the this radical. Now there are two possibilities there. It can form 5 endoteric cyclization, or you can also undergo four exoteric cyclization. In this case, the 4 exoteric cyclization is involved, that can lead to the formation of a benzylic radical. Once you form the benzyl radical, this can be stabilized by this aromatic ring. Once you form this one, this can now react the tributyl tin hydride to give this lactam as the product. As you can see here, the radical reaction plays very important role to construct very complex cyclic systems. Otherwise, it will be very difficult to make by traditional methods. Here, an example shown where you use mercury acetate as a reagent. In this case, as already we know that when you have the alkene, it can react with mercury acetate. You form the addition compound. Once you form this one, this can lead to intramolecular nucleophilic substitution to give this compound. Since it is a leaving group, via SN2 pathway you can form this cyclic compound. Once you form this one, now when you react with this sodium borohydride derivative, which can reduce into this hydride derivative. Once you have this one, now it can undergo homolytic cleavage to give a radical as shown here. Once you form this radical in this reaction undergoes with methyl acrylate, can lead to the formation of this secondary radical. This radical can be stabilized by this ester group. Once you form this radical can react with this. Once we have formed this one, the reaction medium, it can react this hydrogen. It will be converted into and mercury. So in this way, if we have, for example, alkene which has this amino substituent which can be readily reacted with mercury acetate to give this tetrahydropyrrolidine derivative. Once you form this one, this when you react with sodium borohydride salt, and it can convert into this radical. Once you have the radical, that can lead to addition reaction with alkenes to give the radical. That radical again can react here. In this way, you will be able to form valuable cyclic compounds. In this, you form first carbon-carbon bond via nucleophilic substitution, followed by a carbon-carbon bond via radical pathway. Once you form this one, that can be reacted with this intermediate to give this addition product. Now let us look at the reactions of alkynes. If you have terminal alkyne, the reaction of phenylacetylene shown here, in the presence of copper to acetate and base, you can try to couple the alkyne to give this dimerized compound. In this reaction, the copper 2 is reduced to copper 1, where you convert this carbon hydrogen bond. This bond is very strong, and when you can use base, you can deprotonate. You have this carbon ion which can be converted into radical, where copper 2 will be reduced to copper 1. Once you form this radical can undergo dimerization to give this compound. This reaction has wide application. For example, if you want to make this hexadiene, and it is very difficult to make by other method, you can use this 1,5-hexadiene, and this you can try to react with copper acetate in the presence of pyridine. You can make this cyclic trimer. So in this reaction, the copper 1 acetate is first oxidized to copper 2 acetate. The reaction is carried out in the presence of oxygen. Once you form this copper 2 acetate, as we have seen, the pyridine can deprotonate this proton. You deprotonate this hydrogen, you form the carbon ion. So once you form this one, that will be converted into radical. So that can couple two radical here. Similarly, here 3 molecule of 1,5-hexadiene can have coupled together to form this cyclic trimer as the product. Once you form this one, now you can try to deprotonate using base followed by hydrogenation. You'll be able to form this. In this case, the formation of 18 aniline shown here. If you have this 1,5-hexadiene, which can be readily converted into 18 aniline using this approach. And first, what happens here, when you use the copper 1 acetate, is oxidized to copper 2 acetate, which can reduce the anion that you generate from the alkyne using base to radical that can undergo trimerization as shown here. You form the cyclic trimer of 1,5-hexadiene. Once you form this one, when you have the base, it can deprotonate, followed by, when you do the hydrogenation, you will be able to form this 18 aniline as the product. Now let us look at the Acyloin condensation. This is also very important transformation in synthetic chemistry. Already all of you know very well, if you have the ester, it can be converted into hydroxyketone as shown here. What you do here, you make a couple this to, you form this compound, you make a carbon-carbon bond. The mechanism of this transformation shown here, sodium can give 1 electron and you form this radical. Once you form this radical, which can undergo dimerization, you get this compound. Addition of coupling of two radical can lead to the formation of this compound. Once you form this salt, which can readily convert into sodium ethoxide and the diketone. Once you form the 1,2-diketone, and 2 equivalent of sodium can give 2 electrons. You can see here, you form 2 electrons, then you form this intermediate, which can couple together, you form this salt. Once you form this salt, now when you do protonation, can form this diol, which can convert into alpha hydroxy ketone as a product. So this about, if you have the ester, you can couple, you will be able to form this Acyloin as a product by transfer of electron. In this you need 4 equivalent of sodium, and they can form this compound. Now let us look at this diester, which can be cyclized using this approach. Using sodium in xylene solvent, you can get this macrocyclic ketone derivative as a product. As we have seen, you can try to, when you react with sodium, you have to use excess sodium, 4 equivalent of sodium. First, when you use 2 equivalent of sodium, it can convert into it can give 2 electron. Once you have this one, it can couple together, you will be able to form you form this one. Once you form this, this can, as we have seen earlier, you will lose methoxide, and which can lead to the formation of this diketone. And once you have this one, when you add sodium, it can give electron, can convert into so when you do the protonation, this can convert into this derivative. In this way, you will be able to, if you have the diester, the presence of sodium, you can convert in cyclize to give this alpha hydroxy ketone as the product. Similarly, in this case, you have the this diester, and you have the carbonyl group which has been produced by ethylene glycol. Once you have the acetal protecting group which is stable under these conditions, and you can try to react with sodium in toluene, and you will be able to form intermediate. You can couple this to ester group, and which can be trapped when you have the here you have done here when you quench with proton, you get the diol. Instead of that, you can use 2 equivalent of trimethylsilyl chloride. So once if we have in this case once form this, you have the ketone. Once you form the ketone, now when you add sodium, you form the which can convert into so this when you react with 2 equivalent of trimethylsilyl chloride, you will produce the corresponding ether as the product, which can now undergo reaction, and you will be able to form the silyl ether as the this is stable under basic conditions. Now let us look at the oxidation of this halo substrate, and here when you react with this reagent, and in this reaction this acts as a radical initiator. We have seen so far the use of AIBN, the tin based chemistry. Here when you heat this azo derivative, it can undergo homolytic cleavage. When you heat it, you form this tertiary butoxy radical. Once you form the tertiary butoxy radical, this radical can react with this tin reagent. You form the tributyl tin radical. Once you form the tributyl tin radical, already we have seen, if you have the carbon halogen bond which can readily react, you form the secondary radical. Once if you have the radical, you have the sulfonyl acide which can undergo cleavage here. This radical and this radical, you will be able to get the acide derivative. So in this way, for example, if you have this bicyclic lactone which has the halogen substituent which can be readily reacted with this sulfonyl acide in the presence of tin reagent, where we use this as a radical initiator. This can react with the tin reagent. You form the tributyl tin radical. Once you form this one which can readily react with this carbon iodine bond, it can undergo homolytic cleavage to give the radical. This radical can react with this sulfonyl acide to give this alkyl acide as the product. In summary, in the first part of the lecture we have studied the use of samarium, copper and manganese based systems for the radical cyclization that can lead to the complex cyclic compound. If you look at the reactions, you have to use stoichiometric amount of samarium and manganese based systems. The samarium based chemistry widely used for the keto compounds. If you have the ketone, you can form the ketyl radical, where samarium is converted into samarium 3 by single electron transfer process. And once you form the radical, that radical can be reacted. If you have the alkene, it can undergo addition reaction. Once you have the radical, that radical can be further reduced by samarium into carbon ion, where samarium 2 is converted into samarium 3. We have seen some examples. Once we have the carbon ion which can be protonated, then we have seen the manganese based reactions. This is usually used if you have the 1,3 dicarbonyl compound, you form the radical. That radical can be used for cyclization reactions. We have seen several examples. Then we have seen some examples using copper based systems, where you need catalytic amount of copper. We can use peroxide, which can convert into radical, that can initiate the reactions. We have seen some examples. Then we have seen the tin based reactions. We have seen several examples. You have to use a radical initiator in these reactions. You can form the radical from the radical initiator. Usually, mainly we have seen the use of AIBN, which can be readily cleaved into radical in the presence of light or heat, that can further react with the tin reagent. We form the tin radical that can be reacted with, if we have the carbon halogen bond, which can readily undergo reaction to homolytically cleave. You form the tin halide, where you generate the carbon center radical, which can be further utilized for the addition reactions. At the end, we have seen the Acyloin condensation. This all of you know very well. If you have the ester, they can be coupled using sodium. Sodium can give one electron. You form the radical anion, which can, the radical can couple together, so that you can convert into alpha hydroxy ketone as a product. We have seen some examples. So as we have seen, as all of you saw, these radical reactions can be used to construct complex molecules with excellent stereoselectivity. We have seen several systems where you can construct a fused cyclic systems, otherwise it will be very difficult to make by traditional methods. With this, we conclude this lecture. Thank you very much.